The granite in the Great Pyramid, if you look at the famous King's Chamber, its walls and its roof, the ceiling of the King's Chamber, are all made with gigantic granite blocks.
For more than a century, one question has lingered at the heart of ancient Egypt. And the strange thing is that it was never really about the pyramids themselves, at least not in the way most people imagine. People love to focus on the scale of those monuments, on how many blocks were moved, how they were aligned, and how a civilization so ancient could create structures that still dominate the imagination. But the deeper mystery was never the limestone. The deeper mystery was always the granite. Because granite is where the official explanation begins to feel less like a solid answer, and more like a story repeated so many times that people stop noticing how fragile it really was. When you step inside the King's Chamber of the Great Pyramid, you are not looking at rough, improvised stonework. You are looking at massive granite blocks that were hauled from far away and shaped with a degree of control that still unsettles engineers today. When you look at the Valley Temple at Giza, you find joints so precise that the boundary between one stone and the next almost disappears. When you examine ancient drill cores recovered from Egyptian sites, you see deep spiral grooves cut into solid granite with a consistency that feels disturbingly mechanical. The more closely you study the stone, the more it begins to whisper the same unsettling idea. Whatever happened here was far more sophisticated than the usual explanation makes it sound. And that is exactly where the mystery begins to tighten. Because according to the standard story, the ancient Egyptians achieved all of this with copper tools, stone pounders, patience, and sand. That explanation has been around for so long that it has almost taken on the force of tradition, as if repeating it often enough somehow turned it into proof. But the closer you look at the granite itself, the harder it becomes to accept that this explanation is complete. Granite is not soft, and it is not forgiving. It is packed with hard mineral components like quartz and feldspar, and those minerals do not quietly yield to weak tools or simplistic methods. Even today, with modern equipment, working granite is slow, punishing, expensive, and technically demanding. It wears down tools, magnifies mistakes, and resists easy control. Anyone who has ever worked with it will tell you the same thing. Granite fights back. And yet more than 4,000 years ago, the Egyptians were not merely breaking granite apart. They were shaping it, flattening it, drilling it, smoothing it, fitting it, and turning it into chambers, statues, sarcophagi, columns, boxes, and surfaces so exact that some of them still look, at first glance, as though they were machined. That is the part people tend to glide past too quickly. It is not just that they worked hard stone. It is that they worked it with control. They worked it with repeatability. They worked it in a way that suggests they understood not only force, but material behavior. That is why the real question is not simply whether ancient people could cut granite at all. Of course they could damage it. Of course they could chip it, pound it, and slowly abrade it. The real question is whether the accepted methods can actually account for the speed, finish, geometry, and consistency left behind in the stone. Those are not the same thing. Proving that something is technically possible under crude conditions is very different from proving that it plausibly explains the actual artifacts we see. That gap is what kept haunting the granite problem. Over the years, engineers, stonemasons, and experimental archaeologists kept circling back to it, because every time they tried to take the official explanation seriously and reproduce it under realistic conditions, something felt wrong. Copper tools wore down quickly. Sand did abrade, but painfully slowly. Stone pounders could bruise hard rock, but they could not explain the precision. The cuts produced in modern experiments often looked rougher, slower, and less controlled than what survived from ancient Egypt. And that mattered, because the Egyptian evidence was not merely about removal of material. It was about controlled surfaces. It was about straight cuts, circular drill holes, flat planes, and joints so tight they still provoke disbelief. Manufacturing engineer Chris Dunn was one of the people who looked at this evidence and did not respond with casual admiration. He responded with alarm, because from the perspective of someone trained in precision machining, certain details in ancient Egyptian granite do not simply look impressive for their time. They look technically serious. They suggest process control. They suggest deliberate method. They suggest a level of understanding that feels out of step with the picture of soft copper scraping helplessly against stubborn stone, while sand does the rest. That old explanation always sounded reasonable at first. Copper is soft, yes, but the argument was that the copper itself did not need to do the cutting directly. It only needed to carry an abrasive, with sand acting as the true cutting medium. On paper, that sounds plausible, but the trouble begins the moment you actually test it. When researchers used copper tools with sand against granite under controlled conditions, progress was painfully slow, tool wear was heavy, the resulting surfaces were rough, and the marks produced did not convincingly match the cleaner evidence seen on ancient artifacts. That does not mean sand was useless. It means sand may not have been enough. And that distinction changes everything. Because possible is not the same as plausible, and a method that technically works in the loosest sense is not automatically a satisfying explanation for one of the greatest stoneworking traditions in human history. If a process removes material so slowly, so crudely, and with such poor control that it struggles to resemble the archaeological evidence, then something is missing. For a long time, that missing piece remained just out of reach, which is why the granite question never really went away. Then, the story took an unexpected turn, and it did not happen in a tomb, a buried chamber, or a museum archive. It happened in a materials lab. That matters more than it may seem at first, because granite is not only an archaeological puzzle, it is a materials problem. It is a wear problem, a friction problem, a surface interaction problem. In other words, it belongs not just to historians, but to people who study how hard materials respond under pressure, abrasion, and controlled mechanical action. In 2022, Graham Hancock worked with Dr. Masood Garb, a specialist in tribology, the science of friction, wear, and how surfaces interact under stress. Dr. Garb was not approaching the problem as someone trying to defend a traditional Egyptological narrative. He was approaching it as a materials scientist looking at physical evidence and asking a direct question: what kind of cutting system would actually leave behind these marks? Under a scanning electron microscope and with chemical analysis, he examined ancient granite cutting surfaces, expecting, as many people had for decades, to find ordinary evidence of simple abrasion, perhaps sand, perhaps copper residue, perhaps the familiar fingerprints of a crude but persistent ancient process. That is not what appeared. Instead, the microscopic evidence began to point somewhere far more interesting. The wear patterns did not behave the way ordinary sand-based abrasion should behave. The scratch signatures were not telling the expected story. The residues embedded in the grooves did not support the comforting old picture. And then, inside those ancient cutting traces themselves, something appeared that should have changed the entire conversation the moment it showed up under magnification. Corundum. That was the shock. Corundum is aluminum oxide, and on the Mohs hardness scale, it sits at 9, just beneath diamond. It is one of the hardest naturally occurring materials on Earth. Rubies and sapphires are forms of corundum. In the modern world, corundum is used constantly as an industrial abrasive because it is brutally effective at cutting hard materials. And now traces of it appeared inside grooves, cut into Egyptian granite thousands of years ago. Not loosely scattered across the surface. Not floating in random dust. Not resting nearby where contamination could be easily assumed. Embedded inside the grooves themselves. That single detail had enormous implications. Because if copper was not acting as the primary cutter, but instead serving as the carrier or guide for a much harder abrasive slurry, then the impossible suddenly stopped looking impossible. Copper no longer needed to overpower granite directly. It only needed to hold, guide, and deliver particles hard enough to do the real cutting. In that kind of system, the softness of the copper ceases to be the fatal weakness critics assume it must be. It becomes part of a more intelligent arrangement. The abrasive does the work. The tool controls the action, and once you see the problem that way, the whole granite mystery begins to rearrange itself. Suddenly, the old failed demonstrations with ordinary sand make sense, because they may have been testing the wrong abrasive all along. But even then, an intriguing microscopic discovery is only the beginning. It can point, suggest, and provoke, but it does not close the case by itself. The next step was the one that really mattered, because if corundum-based slurry had truly been part of the ancient method, then the theory should survive contact with experiment. It should perform differently from the standard model. It should cut more effectively. It should generate tool behavior and groove signatures that begin to resemble the actual Egyptian evidence. That is where things became much harder to dismiss. In controlled trials, granite was worked using copper tools combined with different abrasive systems. Researchers tested ordinary sand, quartz-rich mixtures, and then a slurry that incorporated corundum. The contrast was not subtle. Sand was painfully slow, Quartz mixtures were only marginally better. But once corundum entered the process, the entire behavior of the cutting system changed. Cutting speeds rose sharply, tool wear dropped, the action became smoother and more stable. The copper stopped behaving like a weak edge, doomed to fail against hard stone, and instead began behaving like what it may always have been in such a system, a guide for a far harder cutting medium. And the drilling results were even more striking. For years, one of the most puzzling pieces of evidence in ancient Egyptian stoneworking had been the spiral grooves visible in ancient drill cores. Those grooves do not look random. They suggest organized advancement into the stone, a repeated cutting action that engineers found difficult to reconcile with the old, slow, inefficient models. But when harder abrasive slurries entered modern replication experiments, similar groove behavior began to appear. That is the kind of moment that shifts a theory from interesting to dangerous, because it means the new model is not merely elegant on paper. It is beginning to behave like the ancient evidence itself. Veteran stonemasons involved in this kind of work describe the difference in almost physical terms. Granite no longer felt like it was being attacked by the wrong method. The process began to make mechanical sense. The copper guided, the abrasive cut, the system stabilized, and what once seemed implausible under one explanation began to look logical under another. That is when the story stops feeling like speculation and starts feeling like recovery, as though a lost technique is briefly resurfacing in front of modern eyes. And maybe that is the most important part of all. Because this is not a story about magic, and it is not necessarily a story about impossible lost machines. It may be something much more unsettling than that. It may be a story about underestimation. If corundum-based slurry really was part of the Egyptian method, then what we are looking at is not crude brute force, but refined process knowledge. It is experimentation, selection, optimization, and control. It is generations of craftsmen learning which materials cut which stones, how fine the abrasive must be ground, how thick the slurry must remain, how pressure changes performance, and how to keep the entire system working efficiently without clogging or collapsing. That is genuine technical knowledge. In a system like this, nothing is casual. Particle size matters. Slurry consistency matters. Pressure matters. Water content matters. Temperature matters. Too thin, and the slurry loses effectiveness. Too thick, and the cut clogs. Too much pressure, and the action destabilizes. Too little, and progress slows dramatically. This is not the kind of thing people stumble into by accident and then scale up across monumental architecture. This is skilled craftsmanship, refined into engineering practice. And, if that is true, then the technological profile of ancient Egypt sharpens in a way mainstream explanations have not fully absorbed. Suddenly, the Egyptians are not merely labor organizers moving stone with determination. They are materials experimenters, process optimizers, and highly trained specialists working within traditions of practical knowledge that modern observers only partially understand. They would have needed not only to recognize the usefulness of an unusually hard mineral, but to process it into effective grain sizes, apply it in controlled slurries, and integrate it into stoneworking at scale. That implies refinement. It implies training. It implies craft traditions. It may even imply trade networks sophisticated enough to acquire abrasive materials unavailable locally in useful form. And once you follow that line of thought, the implications grow larger than one mineral and one workshop experiment. Because now the question is no longer simply, how did they cut granite? Now the question becomes, how many other ancient techniques have we misread because we assumed ancient people had to be simpler than the evidence suggests? How many times have we looked at a finished artifact, failed to understand the process behind it, and quietly inserted a weaker explanation just to keep the larger narrative comfortable? That is where the reaction to these findings becomes revealing. Some scientists ask the right questions. Could the corundum traces represent contamination? How widespread are they? Can the results be reproduced consistently? How much of the material would have been required? Is there evidence of trade routes or acquisition patterns that could support long-term use? Those are fair questions, and they are exactly the kind of questions good science should ask. But not everyone responded that way. For many critics, the real issue was not the evidence itself, but the name attached to it. Graham Hancock had spent decades being dismissed as an outsider, and for some people, that was enough to make the conversation end before it began. In that kind of reaction, the microscopy does not matter. The replication does not matter. The mechanics do not matter. The possibility that the old explanation may be incomplete becomes secondary to the social discomfort of allowing the wrong person to be associated with a meaningful correction. And that reveals something deeper than a debate about ancient stonework. Sometimes the greatest obstacle to new understanding is not the lack of evidence. It is the politics of authority. It is the quiet assumption that certain people are allowed to challenge established stories, while others must be ignored even when the physical evidence begins to move in their favor. None of that means every controversial theory suddenly becomes true, and it certainly does not mean every broader claim made by any one figure deserves acceptance. Evidence has to stand on its own. But that is precisely why this case matters. The corundum hypothesis does not ask anyone to abandon reason. It asks them to look more carefully at the physical traces already present in the stone, and to admit that the old explanation may have been too simple for the evidence it was supposed to explain. That is what makes this discovery so compelling. Because it does not merely add a detail to the story of ancient Egypt, it changes the tone of the entire civilization. If the Egyptians were using corundum-based abrasive systems, then they were not just monument builders with patience and manpower. They were people with a much more advanced practical understanding of hard materials than later scholars assumed. They were not primitive craftsmen struggling against stone with inadequate tools. They were intelligent specialists working within a technical tradition that may have been far more sophisticated than the categories we imposed on it. And if that is true, then the real discovery is bigger than corundum. The real discovery is that the evidence may have been in front of us for decades, preserved in grooves, drill cores, wear patterns, and cut surfaces. While everyone kept repeating a weaker story because it was familiar and easy to teach, the stone may have been telling the truth the whole time. The cuts were there. The patterns were there. The embedded residues were there. We simply did not look hard enough, or perhaps we looked, but were too committed to the old narrative to see what the evidence was trying to say. That is why this question continues to linger long after the microscope and the workshop tests. Because once one overlooked abrasive can force us to rethink the technological profile of one of history's greatest civilizations, the silence around other ancient methods becomes impossible to ignore. If one microscopic trace can reopen a problem people thought was settled, then what else are we still getting wrong? What other techniques are preserved in plain sight on ancient surfaces, dismissed because they do not fit the story we are most comfortable telling? Maybe the ancient Egyptians were never doing the impossible. Maybe they were doing something more unsettling than that. Maybe they were doing something deeply intelligent, carefully refined, and technically sophisticated, while later generations kept insisting they must have been simpler than the evidence allowed. And if that is true, then the granite was never silent at all. It was speaking through every groove, every polished surface, every drill core, and every precise cut. The mystery was not that the evidence was missing. The mystery was why it took so long for anyone to listen.